These two tomato examples use exactly the same nutrient targets, fertilizer products, concentration factor, and stock tank volume. But CropFeed produces very different fertilizer quantities. The only input that changes is the irrigation water. In this tutorial, we will build both recipes from real sanitized CropFeed screens and explain every important difference. A fertilizer recipe that works with one water source may not reproduce the same solution somewhere else. Source water can contribute calcium, magnesium, sulfate, nitrate, sodium, chloride, and alkalinity before any fertilizer is added. That starting chemistry changes both the missing nutrients and the way multi-nutrient fertilizer sources must be combined. Begin with a laboratory irrigation water analysis. Water pH is useful, but pH alone does not tell us how much acid the water will consume. CropFeed needs the measured ion concentrations, especially bicarbonate or alkalinity, calcium, magnesium, sulfate, sodium, and chloride. Use the reports units carefully and convert them before entering values when necessary. The first sanitized profile is low mineral water. It contains 1.20 millimoles per liter of bicarbonate, 0.30 calcium, 0.15 magnesium, and 0.10 sulfate. Its calculated water EC is 0.14 millisiemens per centimeter. Most of the final tomato solution must therefore come from fertilizers. The second profile is mineral well water. It contains 6.20 millimoles per liter of bicarbonate, 1.80 calcium, 2.00 magnesium, and 0.30 sulfate. Its water EC is 0.74. Sodium and chloride remain the same as the first profile, so this comparison isolates the mineral and alkalinity differences. The two water cards show a clear EC difference, but EC by itself cannot tell us whether that conductivity comes from useful calcium, unwanted sodium, bicarbonate, chloride, or another ion. Use EC as a monitoring signal, then use the complete water analysis to build the recipe. That distinction prevents a simple number from replacing the chemistry. For both runs, the concentration factor is 100, the stock tank volume is 1,000 liters, and nitric acid is selected. The residual bicarbonate target is 0.60 millimoles per liter. Keeping those settings identical lets us attribute the changed quantities to the source water rather than to tank size, injector ratio, or acid choice. The shared tomato target includes 17.00 millimoles per liter of nitrate, 9.00 potassium, 5.50 calcium, 2.00 magnesium, and 1.50 phosphate. These values are a sanitized teaching example, not a universal crop recommendation. Real targets must reflect cultivar, stage, climate, substrate, and management strategy. Both runs use the same 6 sources: calcium nitrate, ammonium nitrate, potassium nitrate, potassium sulfate, monopotassium phosphate, and magnesium sulfate. This matters because each product contributes more than one ion. The solver is not filling independent boxes. It is balancing a connected system in which changing one source can move several nutrients at once. With low mineral water, CropFeed calculates 6.00 kilograms of nitric acid, 112.37 kilograms of calcium nitrate, and 45.57 kilograms of magnesium sulfate. The low starting calcium and magnesium explain why these fertilizer quantities are high. The calculated final EC is 2.62 millisiemens per centimeter. The low water result also demonstrates why the complete balance must be reviewed. Magnesium sulfate is needed to reach the magnesium target, but it brings sulfate with it. With this product set, sulfate finishes 0.71 millimoles per liter above target. CropFeed displays that remaining difference instead of pretending every target was matched exactly. On the check page, the low water recipe reaches 9.00 potassium, 5.50 calcium, and 2.00 magnesium, while sulfate is 3.71. This is the moment to decide whether the result is acceptable or whether the targets, fertilizer sources, or operating assumptions need to be revised before mixing. Now we return to the calculator and change only the selected water profile. Mineral well water has a higher EC and begins with more calcium, magnesium, and bicarbonate. The crop target, 6 selected fertilizers, 100 times factor, 1,000-liter tank, residual bicarbonate setting, and nitric acid selection remain exactly the same. With mineral well water, nitric acid rises to 56.00 kilograms because substantially more bicarbonate must be neutralized. Calcium nitrate falls to 79.96 kilograms because the water already supplies calcium. Magnesium sulfate falls to 0 because the starting water already contains the complete 2.00 millimoles per liter magnesium target. The difference does not stop with calcium and magnesium. Potassium nitrate falls from 40.20 to 21.51 kilograms, while potassium sulfate rises from 30.66 to 46.77. Monopotassium phosphate stays at 20.40. Nitric acid contributes nitrate, so the solver shifts the potassium sources to preserve the shared nutrient targets. Between the two sanitized runs, nitric acid changes by 50 kilograms, calcium nitrate by 32.41 kilograms, potassium nitrate by 18.69, potassium sulfate by 16.11, and magnesium sulfate by 45.57. Those differences belong to this exact water, target, product, factor, and tank combination. They are not transferable application rates. The mineral well water run matches the entered targets with this fertilizer set. Its final EC is 2.55 millisiemens per centimeter, and the calculated potassium to calcium ratio is 1.64. Matching the targets mathematically is still only one gate: product purity, solubility, compatibility, injector calibration, and crop response must also be checked. The reliable workflow is simple. Test the irrigation water, enter the measured ions in the correct units, choose targets appropriate for the crop and stage, confirm the available products and operating settings, solve, and review the complete balance. CropFeed helps organize that process and compare scenarios. Build smarter nutrient solutions with CropFeed, available for Android on Google Play.